Hello kids, today we are going to be discussing Unit 3 for Grade 8 Science, which is Force and Energy. In that chapter we have the first subtopic, which is density. So let's discuss what density is. So when you look at this diagram, it's a bowl which is filled with water, and this you can see that there are several articles over here. We've got wood, we've got cork, which is also wood, but it's a lot more porous. Then we have oil, we have dish soap, we have iron nail, and we have a metallic coin, right? So some of these things are floating, and some of them are sunk, and this is what you call as suspended, right? It's suspended. It's not totally sunk in it, but it's still somewhere in the middle, which we call as suspended, and these are floating, right? So we call this as float, right? This as suspended, and these as sunk, right? So once you look at this, you understand that there must be some difference in these materials, that some of them are floating and some of them are sinking. So this is a basic idea of how we can compare density of different materials compared to water, right? Because water is an ultimate, you can say, a standard for measuring the density. So what is density, right? So what is density? So density, it is the measure of how heavy or light an object is, right? And obviously, if it's lighter, it will float on water, and if it's heavier, it would sink in water. Now, this is just a basic definition, right? We're going to go deeper into this. I'm going to express density in a different manner, right? I'm going to write a different definition, right? Uh, it is, sorry, it's a little too, there we go, right? It is the packing factor, or it is the packing of particles of an object, right? How well packed uh, those particles are, we say that it has become dense, and how loosely they're packed, we say it's less dense. So what is density? It is the ability to define an object in terms of its packing, right? Packing of the particles, or or for a non-scientific manner, we can say how heavy or light an object is. So what is density, right? We define density by a very simple formula, right? Density is equal to uh, how much mass an object has and how much volume or space does it occupy, right? And we do know that the unit for mass that we use for lab scales is grams, right? And when we talk about volume, we are going to be using centimeter cube for this, right? And density is going to have the units of gram per centimeter cube, right? So it is grams per centimeter cube, which is the unit, right? But this is for the lab scale work. When you go, for larger scales, we use kilogram per meter cube. Now, to help you understand much better what density really is and how the states of matter relate to the density of materials, just have a look at this diagram, right? I'm going to zoom it up a little bit. Now, as you can see over here, right, that in gas the particles are far away. They're able to move freely. Hence, they're not very well packed, right? So it is less dense. Then we have a liquid in which the particles are close to one another, but you still get to find some of these spaces in between. So we say it is dense, but obviously not compared to the solids. When you look at the solids, the particles are extremely packed. They're only able to vibrate, and over here we say that the density is very high, or the packing is very high, Now I've marked out three of these important ones, right? For example, over here you have oxygen, which we breathe. It has a density of 1.43 kilograms meter cube, or you could say it's 0.00143 grams per centimeter cube, right? So conversion from kilogram uh, per meter cube, 1 kilogram per meter cube is equal to 0.001 gram per centimeter cube. I mean, that's the basic idea, that you simply divide the value in kilograms by 1,000 to get to grams per centimeter cube, right? That's a simple converter for this. Now, over here we have water for liquids as an example, which has a density of 1,000 kilograms per meter cube, or as I said, you can simply divide it by 10, so it is going to be 1 for water. As I said, water is the standard, so we take density of water as 1, and then we build up or compare other materials with water to find their densities. Now, when you look at solids, steel, which is one of the most common materials that we see around, uh, iron, you can say, right? So that has a density of 7,500 kilogram per meter cube, or 7.5 gram per centimeter cube, right? So what clear differences do we see right over here? Particles uh, move freely, right? That's the first thing over here. Particles are able to move, but still very close, right, to each other. And over here, particles are jam-packed, right? And when we talk about the movement, over here they're free to move. They have no uh, intermolecular or particular forces, right? Since it's a gas, it is supposed to be in molecules, right? Other than the noble gases, no intermolecular forces. That means there are no attractive forces for these particles to get to to stay stuck to each other. Over here we have uh, low intermolecular forces. That's why they are able to move about or swap places, but they are still not. I mean, these intermolecular forces are still there. Hence, it cannot just float around like a gas. And finally, in particles, high intermolecular forces, right? Or high particular forces. The particles are attracted to each other at a very high rate, or you can say with a lot more force. So this is the basic idea, the difference between these three states of matter relating to the density. Now, as you can see over here, the gases are going to have the least density, then the liquids, and then the solids. Now, even in liquids, we have a few, examples which are a little off the chart. For example, liquid mercury, which is a liquid metal, has a density of 13,534 kilograms per meter cube, or 13.5 gram per centimeter cube, which is 13 times more heavier than water. So you can imagine that the liquid mercury, if we had liquid mercury, and I put a steel bar in a liquid mercury, the steel is going to be floating on mercury. Why? Because the density for mercury is a lot more higher, which we see over here. Now, if we compare this chart over here with this diagram that we had, now we can simply say, why did the iron nail, is sunk? Because it has a lot more, it's a lot more denser compared to water. And why this oil or wood is floating? Because these have probably lesser density values compared to water. And if we compare dish soap, then we can say that it is slightly heavier than water, right, or slightly denser than water, but it's not as dense as the metals, right, the coin or the snail over here, right? So when we compare, when we talk about any object being sunk or being floating, right? You need to understand whatever the liquid that you're having. In this case, we were using water, right? So the density values for the liquid and the solid that you're trying to study, that needs to be understood, right? If the solid has more density value than water or the liquid that you're trying to check, then it is going to sink. And if the object is going to have less density value than water or the liquid we're studying, then the object will be floating, right? So it's all about the comparison of these density values. These are some examples of the density values, but as I said, these are all in kilograms per meter cube, so we're going to have a unit converter for this. I'm just going to give you this basic unit conversion, right? So we do know that uh, 1 kilogram per meter cube, right, is going to be 0.001 gram per centimeter cube. And why is that so? Because we do know that 1 kilogram has 1000 grams, right? On the contrary, 1 meter cube, which is the volume, right, how much area it is having, is going to be 1 million centimeter cube. Now when we join them together, right, if you say 1 kilogram per meter cube, then it is going to be 1000 grams divided by a million centimeter cube, right? uh, we're going to cross off these 3 zeros, right, from here, and we're left with 1 over 1000 grams per centimeter cube. And that's what I meant when I was saying that when you're changing from kilograms to gram per centimeter cube, you just simply need to divide by 1000, which can be written as 0.001 gram per centimeter cube, right? In general, since air is a combination of several gases, right, including carbon dioxide, which is a heavier one, so the density of the air is actually 0.0014, right? So I'm just going to write the density of air is 0.0014 gram per centimeter cube, right? And the density of water, right? Two common objects that we survive on is 1.00 gram per centimeter cube. Now this 1.00 is for pure water. We're not talking about the water that we drink or we consume every day, because that has added salts to it, which slightly increases the density of the water. And that's the very reason that you would hear that it is very hard to sink in sea waters, because they are very saline, right? They have a lot of salt dissolved in it, so the density is a little higher than pure water. And since the human body averages out to a density a little lower than the density of water, hence it is possible, I mean scientifically it's not possible for a human to sink in seawater, right? And you would find that there are many lakes as well which are extra saline, and it is impossible to sink in those or even swim or dive in those waters, right? Swimming may be possible, but diving would not be possible, because water is simply going to push you out since you're lighter. And that's why we see that air bubbles also come up, or lighter objects float up. If even if you just push them into the water, it is just simply going to rise back up. Why? Because the density is lower. Right. Now moving on to the next topic, which is kind of more fun, right? This is heat and temperature, and it's a very controversial topic, as these two terms, heat and temperature, there are seemingly the same, but they're entirely two different things. So when I say temperature, right? So temperature, I call this as uh, the measure of hotness or coldness, right? That's the basic simple definition that we give, but that's the basic definition, right? So I'm going to write another one. I'm going to call temperature as uh, the measure of uh, current energy of particles in an object. And why I'm writing this advanced definition is because we just saw in density that the particle movement is related to density, right? And we do know when we have three states of matter like the solid, the gas, and the liquid, as the diagram is telling you that the particles are packed. Over here, the particles are a little farther, but they're able to move about. And in gas, the particles entirely free to move about, the independent, right? So definitely, when we talk about ice, it is cold, right? As we said, coldness and hotness. So this is 0 degrees Celsius, right? Let's call this 25 degrees Celsius, which is room temperature. And then for boiling, or these vapors to arrive from water, let's call this 100 degrees Celsius, right? So over here you can easily compare that when the temperature is low, that the particles energy is less, hence they are not able to move about. And when the temperature is rising, the particles are able to move, they have energy to move about. And when we talk about gas, they're able to move up. Why? Because the density becomes lower as the temperature goes up. Things expand. Then the gas is going to fly up, and that is when we say that the particles have a lot of energy, enough energy to escape the liquid, right? So this is what temperature is. But now let's compare what you know heat is. But before that, I'm going to discuss this object over here, which is a thermometer. This is a classroom thermometer. I've shown you one in the lab, right? It was wooden thermometer fixed on it. And why this one is different from the usual thermometers that we see? Because it is supposed to be a fixed display meter, right? The Compared to the ones that we use at home for medical purposes, right? They are much more simpler in design, because we need to place that in the mouth to check the temperature of the mouth, right? So for this is just a lab scale thermometer. It's the same design, except it's just framed up in a bigger place so that it's much more easily visible, right? Okay, when we talk about temperature, we say that it is again the measure of the current energy of the particles. That means the more the energy, the higher the temperature is going to be. The less the energy, the less the temperature is going to be, right? Or conversely, we can relate the temperature with the energy of the particles, right? Now, this thermometer is a device, right? I'm going to write this down. So, what's a thermometer? So, over here, let me just define this, right? Thermometer is a device used to measure temperature, right? But how does this device work? As you can see in this in the lab as well, we saw that when this bulb or this sensor is heated up, uh, we see that this liquid inside, right, which is liquid alcohol or mercury, right, it rises up, right, with the rise in temperature. And why is that so? Because I just explained that when the particles are going to have more energy, then they're able to move about more. Hence, they start to induce these gaps in between these particles. Compared to this, as you can see, it's all fixed up. Right over here, we have now more gaps. So these gaps means that the liquid is going to expand. Right. So from cold to hot, things expand, right? And that is common with with solids as well as with gases. So all three states of matter are going to expand with the increase in energy. I'm just going to show you a simulation how it does, how the temperature is going to affect, or the hotness or coldness is going to affect the particle movement, and how things are going to expand, right? So I'll be discussing that in a moment, but for now, just consider the fact that when you move from hot to cold, things expand. And when you move back from hot, let me just change the color so that this doesn't get any confusions. From hot to cold, uh, things contract, right? So that means if I'm going to cool this bulb down, then I'm going to see a drop in the temperature reading, right? So this is how we use temperature as a measure for the energy and the particles. And what is heat? Now I'm just going to define heat over here before I move into uh, the examples, right? So what is heat? So heat is the amount of energy that the particles have to move about, right? So this is the energy that with which the particles are going to be moving. To measure, I wouldn't say measure, I would say calculate. To calculate heat, and you do understand the difference between calculate and measure. That measure is something that we physically measure, and calculation is what we use mathematical formulae to use our measurements to calculate another physical quantity like heat, right? It's an energy. So to calculate heat, we measure temperature, right? And that's how we relate. In short, I gave you this advanced idea that kinetic energy of the particle is directly proportional to the fourth power of temperature, right? It's just a basic idea how temperature is directly related to the kinetic energy of the particles. The greater the temperature, the greater the energy. The lesser the temperature, the lesser the energy. Now over here, I did discuss some scales, right? So I will be discussing some scales, temperature scales, but before that, let's have a look at these examples. These are the three basic medical application thermometers that you see, and there are many other types of thermometers, but I'm just going to discuss these three very common that you see around. This is the expansion thermometer. I'm going to write the name, right? Expansion thermometer. And why? Because we use expansion of a liquid to see the rise in temperature, right? To have a physical display of expansion. This is what we call as an indicator, right? So it's a physical indicator thermometer which expands. So it's the expansion technology that we're using. Then we have over here what we say as electronic, right? Thermometer. It uses a thermocouple to see the changes in temperature, also known as thermocouple, right? Uh, these are also used in temperature sensors, which you see in the car or other in the refrigerator. There are many devices that use these electronic thermometers, what we call as thermocouples, to identify the temperature and operate. And this is the final one, which we usually use as the optical uh, thermometer, right? Why optical? This is a non-contact thermometer. So you let's just say if you have a patient uh, that has some contagious disease, so you're not going to insert these two thermometers, which are contact thermometers, right? So I'm just going to separate them, right? And this one, right? So these are contact based thermometers, and this is a non-contact, right? So you don't need to touch the patient in any way just to see what the temperature is. It can measure the temperature even without uh, contact with the patient, and hence you know it is better for contagious diseases, right? So this is an optical thermometer, it's a non-contact thermometer, and all of these are medical application, right? So these are medical application thermometers. You can find other types of thermometers, which are industrial thermometers, as well as we have then temperature sensing devices, which are built on these thermocouples, very complex ones for industrial purposes, right? So as I was telling you about the intermolecular forces and density, this is how the intermolecular force can be related to the temperature. If you increase the temperature, let's say from liquid to from solid to liquid, and from liquid to gas, you see an increase in kinetic energy or the temperature. On the contrary, you will find a decrease in the intermolecular forces, right? The molecules were packed here, they had good attraction to each other, then it got a little loose, and in gas there is no more intermolecular force, right? So when we talk about moving towards IGCSE, right? So we need to understand that unit conversion is there, which is not included for grade 8. So I'm just going to go into this additional content. If you don't want to go into this, you can skip the next 5 minutes and move to the next next subtopic. Okay, for unit conversion, we have degree Celsius, degree Fahrenheit, and Kelvin, right? And Kelvin is the SI unit, right? So when we talk about these conversions, degree, any temperature, right? I'm just going to write uh, temperature in degree Fahrenheit is going to be equal to temperature in degree Celsius plus 32, right? Sorry, just a minute. Yeah, right. It would be 9 by 5 plus 32, right? So that means, so whatever the temperature you have at degree Celsius, you need to multiply 9 by 5, which is a conversion factor, plus 32 to get into temperature in degree Fahrenheit. Compared to this, if you have to get temperature in degree Celsius and you're given temperature in Fahrenheit, then the conversion is going to be a little bit different. So it is going to be temperature in degree, degree Fahrenheit minus 32, right? And it is multiplied by 5 by 9, right? So it's a simple mathematical conversion from here to here, right? So if you are given with temperature in degree Fahrenheit or in degree Celsius, now you should be able to convert these two. Now these two are much more common, right? These are common. The degree Fahrenheit is used for medical purposes. Degree Celsius is used for industrial applications. But when we talk about scientific work, then Kelvin is used, right? And for Kelvin, we say that degree Kelvin is equal to degree Celsius plus 273, right? So these are the basic converters that we see. These two are more common, right? But this one is for scientific applications only, right? Scientific work. Now, for advanced O-level topic, I'm going to go into the absolute scale. So I did discuss this in the class that it is impossible to understand that if water, let's talk about water, right? In water, we see that water boils at 100 degrees Celsius, freezes at 0 degrees Celsius, and we have a negative scale, right? So we have negative degrees Celsius over here and the positive above 0. But this is not possible because when we talk about something absolute, that means it starts from 0 towards positive only. So absolute quantities are not supposed to have negative values. For example, if I say height, right? So the height, your height, can it be measured in negative, right? Is it negative? Is it possible to have a negative value for your height? I don't think so. It's not positive. I mean, it's not possible at all, right? Similar way, if we talk about mass, right? How much you weigh, is it possible to have a negative value? No, it's not possible because you cannot be minus 60 kilograms, right? You are definitely positive 60 kilograms. So some of these quantities are supposed to have absolute scales. That means they cannot have a negative value because those are physical measures. So when we talk about temperature, right? If we talk about temperature, we see this negative, right? We do understand that our refrigerators can go to minus 20 degree, minus 16 degrees Celsius. Sorry, the freezers, right? And our refrigerators are able to achieve, 4 degrees Celsius in general, but they can also go to minus 4 degrees Celsius if you just set it up for a lot more colder temperatures, right? So we see this negative sign over here, which is not possible when we talk about absolute scales. So when we talk about absolute scales, we need to have a value that is going to start from 0 and move forward. So when we talk about the lowest possible temperature in the universe, we say that it is 0 Kelvin, right? And it moves forward, right? The temperature scale moves forward. Let's talk about temperature, right? So compared to this, for 0 Kelvin, degree Celsius is going to be minus 273 degrees Celsius, right? And when we talk about 0 degrees Celsius, which is the freezing point, and over here 100 degrees Celsius. Let's take water as an example, right? So for 0, it is going to be positive 3 Kelvin, and this is going to be 373 Kelvin. So if you remember, I just gave you a converter for this, which is this one, right, over here. So I'm going to tell you how I'm using this, I'm converting this. So I'm simply taking the temperature in Kelvin by adding temperature in degrees Celsius with the number 273, right? So that is what we have concluded. So any temperature, let's say if it is this temperature, right, this one we want to convert, it is going to be 100 degrees Celsius plus 273, that is going to be 373 Kelvin, right? So that is how we convert these temperatures. Now this topic is only for those candidates who are interested in going for O levels, right? Because when we look at the work breakdown for grade 8 checkpoint science, then we're supposed to relate the topics from grade 8 to O level topics, so that once you go into O levels you have all the prerequisite information, right? Now moving on to the third unit. Now I'm going to rush through these units, right? So heat transfer, modes of heat transfer. Now we do know that heat is the energy that the particles have, and we measure this as a measure of temperature, right? So when we talk about heat transfer, how energy can be transferred. Let's say you have a bowl of water, right? uh, it's filled with water and you just heat it up, right? You give it heat or energy, it's the same thing, right? And heat is specifically used for thermal energy. It's the another name for thermal energy, right? So when heat is given to this liquid, we see that energy is going to float in, and that energy can be radiated as well, right? We feel that heat as well. Let's say if you start boiling water, then we do understand the temperature of water is going to rise, as well as the fact that some of the heat will be radiated or it would be given out as well. Now if you take the example of this kettle, when we heat it up, it's a metal based kettle. The heat from the stove, this fire, is going to be distributed by this metal, what we call as conduction, right? So I'm just going to write three states of matter, right? Solid, liquid, and gas, right? And the absence of any matter is what we call as vacuum, right? So I'll tell why I'm talking about vacuum. So when we say conduction, it is only possible by solids, right? So in solids we only see conduction, in which the particles are going to collide with one another to transfer this heat energy, right? So solids are going to have conduction. And when we talk about liquid and gas, both of them have what we call as convection. Now, what is convection? It is the movement of high energy particles moving up and low energy particles moving down, right? It is very simple example. Let's just say if you have a room, right? And in the room, we see that there's a heater, right? Heater over here. So when we heat things up, we see that there's an air draft. Hot air goes up, right? Uh, it moves around. It pushes the cold air back in to the heater, right? So this is called the convective cycle, right? Or convective circle, right? Loop. So once the convection is going to happen, right? In convection, we see that hot air is going to move up. And why hot air moves up? We discussed this in density, that when we give energy to particles, or we increase the temperature of any object, we see that the particles move away from one another. That makes the particle less dense. In other words, if we heat a gas, then the particles of the gas are going to move apart from one another, and when those particles are going to get lighter, it is going to expand, and hence less dense air is going to move up, and it is going to push more denser air around downward, and the colder air, which is going to be less energetic, the particles are going to be close to one another, it is going to move downward, right? So this is the convection that we see. This is why wind blows, right? In the day it blows in one direction, and in the night it blows in the other direction, due to the changes in temperature of the environment, right? Now let's talk about conductors and insulators of heat. So when we look at this, we understand that the solids are best conductors of heat, right? Now over here, I will discuss one thing which is missing in this diagram, and for that time, I'll let you, think about it. So over here we have copper, which is a very good conductor, steel, which is uh, a conductor for heat, but not a very efficient one. Gold is one of the best conductors for heat, right? And then we have silver, which is also a good conductor of heat. These are now solid particles, right? And when we talk about insulators, we have objects like plastic, rubber, wood, and glass. And why these are not good conductors of heat, or why we call these as insulators, it involves the movement of electrons, right? And electrons or particles, right? That means we do know that metals have free electrons, right? So that is why they are the best conductors of heat. Now these particles also have electrons, but they are not free to move about. Hence, they are not able to carry the thermal energy that we're giving to move about. So that's the difference between conductors and insulators, right? Now, before I move into the an introduction of the O levels, I'm going to over here discuss a simulation of heat and energy, right? So we're going to go first into states of matter. This is PhET simulations by Colorado University, right? Over here, you can see that at 14 Kelvin, which is a very low temperature, right? I'm going to let's talk about ice, right? So when we talk about ice, at low temperature, if I cool it down, as you can see, the particles are now getting slower. You can see the vibrations that the movement is getting slow, right? And this is very, very low temperature. And once I start to heat it up a little bit, right, as you will see that the particles are now getting more and more energetic as soon as I reach the melting point, right? And currently I'm not at the melting point. This is ice actually. Why these particles are stuck to each other? They're not able to swap places. You can see this particle is moving around, the one I'm trying to chase, but they're not still able to swap places. And that's what we discussed in liquids, that they're able to swap places. I'm going to heat it up a little bit more, and now you can see this uh, little bit expanded. What we discussed, that on expansion we find, and now since it is 1 degree Celsius, so some of the ice is still there. It is melting. As you can see, this is now becoming a liquid. It is starting to lose its shape, and if I heat it a little bit more, you would find that it would convert into liquid as a whole, right? So now these particles are able to swap places. They're moving about, they're rotating, right? I'm going to heat it up a little bit more. Now as you can see, this particle just went from here to here. Now since they're able to swap places, this is what liquid does. And some of these particles that you see moving out, this is what we call as evaporation. Now remember, this is not the boiling point yet. I will discuss what evaporation and boiling is in a moment, but for now you can see over here that some of these particles which were spinning too fast just left the surface area, right? No particle is coming into the air from the bottom, it's only coming from the top, right? As you can see, high energy particles move up, right? Now I'm going to heat it up a little bit more, nearly to the boiling point. Now you will see that the particles are far more energetic. They're moving too fast. They're able to eject more particles into the air. And once I'm going to bring it up to nearly boiling point, you can see these particles are jumping around, right? It's kind of fun to use. And now once I start boiling it, now you can see all the particles are going crazy, and now they are vaporized. They're going out in from the into air. They're moving about freely. Now none of these particles are attracted to each other. As you can see, these are now free particles. This is what we discussed when we were discussing states of matter. So liquid, solid, and gas, right? So when we talk about this is water actually, right? So you can have a look at oxygen molecules, how in the form of liquid it is going to be, and if we try to solidify oxygen, right, and the gas, you can see that even if I heat up a gas, although it is still a gas already in the minus temperatures, but the more I heat it up, the particles become more and more energetic. They start to move faster. The more temperature I increase, the faster they become. In a moment, you'll see how fast they're going to get. They're literally going to get crazy. The collisions will increase. They will collide with one another with more energy, and they're going to impart more collisions and will have more speed. Now you can see that the particles have started to speed up, right? Since it's a gas, so this is going to be very high temperature to make it too fast, because those particles are already free, right? So their kinetic energy is now increasing. Now, as you can see, more collisions are there. Before they were just floating around, now they're colliding more and more vigorously, and they're speeding up. So this is what happens when you talk about changes in temperature and resulting in changes in heat. And what is heat? It is the measure of the energy that the particles have. So this, at 250 degrees, you can see that the particles are far more energetic. And if I go to what you can say, colder temperature, right? I'm going to click the gas. It's minus 160. You just saw that it became very, very slow, right? Now, moving on to our next topic, which is going to be energy transfer. But before that, I'm going to move into a topic which is related to O levels. It is part of the grade 8 science, but I'm going to discuss it in a more advanced manner. Now, this over here is, you can say, the temperature curve, right? This is called T temperature phase diagram, right? Temperature or phase diagram. And what is a phase? That represents, uh, I'm writing diaphragm, diagram, right? Now, what is a phase? It is called a state, right? That's the another name for the states. So we call this as phase, right? In science. So in solid, you can see from minus 40 to 0 degrees, right? Over here, you can see from minus 40 to 0 degrees Celsius, the temperature is in the solid range. So it will remain in the ice at 0 degrees Celsius. It will take some time, right? If you keep on adding heat, if you keep on giving it energy, if you keep on going to heat it up, we're going to find that these particles are going to break apart, and temperature won't be increasing. Why? Because the more heat you give, it will not rise the temperature. Instead, that heat is utilized in breaking these particles free, right? That is what is happening over here. That the intramolecular force, the temperature is not increasing at this point. Why? And because the energy is used in breaking free the particles instead of increasing the temperature. And once all the particles are free, then again we're going to see a rise in the temperature. You can see that now the temperature is rising up, right? At 100, the same thing is going to happen again, right? That means once a liquid is going to start boiling, when water is going to start boiling, you will see that the energy is now consumed by particles to break free and move out into the air as vapors, right? So again, the force is, the energy is used to convert liquid into vapors. That means the little remaining intermolecular forces that still remains between these liquid particles will now consume the energy, so that the particles could get separated and become independent, right? And the gas, which I just showed you, that even gases can be heated up. This is what will happen, that we can keep on heating gas up, right? This is 130 degrees Celsius. And why is that possible? How we can heat water up to 130 degrees Celsius? I mean, this is what we call as superheated steam, right? Over here we have steam, and this is called superheated steam, right? That means it is also water vapors, but these are high temperature water vapors, usually used for turbines or pressurized cooking. We do have pressure cookers at home which boil water, or which uses the superheated steam to cook meat, right? Which you cannot cook at normal temperatures or normal water boiling, right? Which is at 100 degrees Celsius. So we increase the temperature to 130 and up to 150. I've since I've been into the industry, I've seen superheated steam turbines, which can go up to 450 degrees Celsius. It is again water vapors, but at ultra high temperatures, which increases the pressure at a very alarming rate, which is then used to run turbines and create electricity for us, right? So that's how the thermal plants or the thermohydro electric plants are working. Now over here we have liquid, right? So this is melting over here, and this was solid, right? Purely solid, below 0 degrees Celsius. Now this is a temperature or a cooling curve diagram. The same way, if I start to condense it, it needs to be the same, right? It must not deviate if it's pure substance. Now this was for pure substance. Obviously, when we add impurities, let's say if I all salt to this salt to this water, then this temperature curve is going to be a little different. But if I take a pure substance, I heat it up, and then I try to cool it down, the same curve line is supposed to be there. There shouldn't be any differences in heating or cooling, right? The temperature curve is the same for every pure material. Now over here for IGCSE candidates, I mean those who are aspiring to go into IGCSE, right? Have a look at these examples of basic elements. These are elements, not compounds, right? That means these are independent pure elements, and these are compounds. These are also pure substances, but these are compound. That means they're chemically combined. These are chemically independent. And then we have mixtures, which I haven't given you around because defining the melting and the boiling point of a mixture is a little bit different from pure substances. So these two are pure substances, right? Both of them. So when we talk about boiling points, you can have a look that oxygen and the gases. I mean, it's a gas, right? I'm going to write these letter gas. Then we have liquid. Lithium is solid, as you can see at a room temperature. It is supposed to be solid. It's 181. Aluminum is a solid. Calcium is also solid. So aluminum, melts quickly, but boils at very high temperature because it is a very good conductor of heat. It radiates thermal energy very quickly. That's why you see that many of the electronic devices that we have in our houses, including computers or microwave ovens, they have these aluminum blocks attached to them with a fan to cool them down, right? We use aluminum block based air coolers to cool electronic devices so that they don't burn out with consistent use. If you look at calcium, it's having a lower boiling point because thermal properties also differ between metals. Aluminum is a very good conductor. On the contrary, calcium is not. Now, when we look at the compounds, iodine, right? It's a iodine. We have methane, we have sodium chloride, we have sodium carbonate. This is what we call as table salt, right? Table salt. I'll write the name so that you may remember, right? This is table salt, common salt that we eat, sodium chloride, right? Then we have sodium carbonate, which is called the baking soda, right? Carbonate, salt, baking salt, right? That's the baking salt. Sodium carbonate, sodium bicarbonate. I mean, these are used in our daily lives. Then we have sugar. It doesn't have a boiling point. Why? Because once we melt it down in liquid form, it starts to degrade, and even before it could melt, it reacts and converts into other chemicals, right? So it chemically degrades. So that's why it doesn't have a boiling point. Yes, that we may try to boil this up in a vacuum chamber, but that is going to eventually, convert this into a much more different solid, right? It will decompose even faster. So we cannot have a boiling point for sugar. We're still trying to find ways to be able to measure this, but usually sugar degrades after 146 degrees Celsius. Water has melting point of 0 and a boiling point of 100, and conversely this goes for freezing, right? The melting point can be referred to as freezing point, or boiling can be condensation, right? So at any point below 100 degrees Celsius condensation is going to start, and once we reach 100 it is going to be boiling, right? So this was a little bit idea of different modes of transfer. Now I'm going to tabulate the modes of transfer as a summary, right? Over here, that once you see these conduction, it is happening in solids. Convection happens in liquids and gases. Now what was left is radiation. Now radiation is light, right? We get heat from sun through light, but that light is traveling millions of kilometers just to get to us, and it takes about 8 minutes for sun to sunlight to reach us from the sun. So there is no gas or liquid or solid in between us and the sun. Now do not consider the atmosphere of Earth, because that is very localized to Earth. There is nothing between the sun and Earth. There is a huge gap between us two, and there's pure vacuum, right? So when we talk about vacuum, we get radiation, right? That means uh, light or other ways like X-rays, gamma rays, infrared, ultraviolet. So all these are radiations or light-based sources. They transfer energy, thermal energy. They're able to transfer thermal energy without the use of liquid, gas, or solid. But it doesn't mean that it cannot go through them. We do know that light can travel through glass. It can travel through solids if it's transparent. It can also go through liquids if it's transparent. I mean, light can come through water as well, and it can definitely transfer heat, even there if there's a gas, because it's coming all the way from sun through vacuum into our atmosphere, which is a gas covering around the earth, right? That is what we call as the atmosphere, and light still delivers us the heat energy from the sun, right? So that is what we call as a radiation. Now moving into energy transfer. Now I've discussed this topic in very much detail in the class, and we did make a very big, a chart in which I placed energy in the middle, right? So I'm going to just redo this. I wasn't able to find any appropriate diagram for this on the internet, because I haven't seen anyone summarize this the way I'm summarizing this. So energy has several types, in which the most simple one, what we call as mechanical energy, right, or kinetic energy, right, that is there. And then we have you can say thermal, right, or geothermal, the one that we're studying right now, heat energy, right? Uh, then we have chemical energy, right? Energy being released through chemical reactions, right? Chemical reactions, what we call as chemical energy. Oh, just a minute. I got two A's over there. My bad. Okay. Chemical reactions, they also release energy. Usually, chemical reactions release energy in the form of heat, and that heat can be translated into mechanical energy. That is what our car is doing every day, right? Our the engine inside the car, it burns the fuel, it reacts the fuel with oxygen. We ignite the fuel with ignition. The fuel is going to react with oxygen, creating a lot of heat and fire. That thermal energy is translated into mechanical energy of the vehicle, right? And then we have electrical, right? Now you do know that the same thing is done when this engine is running. It is also moving a part we call as generator, right? So generator, right, is going to convert this mechanical energy into electrical energy, and then the same electrical energy again can be converted into chemical energy, what we call as a device using battery, right? So the batteries take this electrical energy, reverses a chemical reaction, and once that chemical reaction is redone, then we can release electrical energy back up, right? So the battery can convert electrical into chemical energy and chemical energy back into electrical energy directly, right? So on the contrary, the engine is converting chemical into thermal, into mechanical, and then into electrical, and then back into chemical energy. That is a big cycle of energy that we have, especially in the hybrid vehicles, right? So this is, you can say, the energy conversion for hybrid vehicles, right? In which the fuel is also there, but the battery is also able to move the car. So we can say that the electrical energy can be converted into mechanical energy, what we call as motors, right? So the motors are simply converting electrical energy into mechanical energy, and then we can convert mechanical energy into thermal energy, what we call as stress, mechanical heating, right? Friction is an example. If you rub two things together, you're giving mechanical or kinetic energy, right, to move the parts. Once they rub on each other, they generate heat, and thermal can be converted into mechanical using an engine, right? We call as combustion engine, and chemical is converted into this using combustion. That's why we call those as combustion engines, because they convert chemical to thermal to mechanical, right? So hence the name combustion engine, right? Okay. How thermal can be converted into chemical reactions? These are some, chemical reactions. Very few of them. We call those as, endothermic reactions, where we have to give heat for a reaction to occur. On the contrary, exothermic reaction, as the name says, exo means exit, so the energy is going to exit, right? Now, these are few of these types. There are other types of energies in which we have a light energy, right? Optical energy, what you call as radiation, that is also able to deliver heat to us, but light itself has a specific energy which we use in solar panels, right? That phenomenon. Now remember, solar panel is not taking thermal energy from light, right? Light can deliver thermal energy, but so far we have understood that the solar panels are not able to withstand high temperatures, one thing, and secondly, once the temperatures go up for the solar panels, their efficiency reduce. That means we're not actually using thermal energy directly from the light. Instead, it is the collision of these of light on a special material that generates electricity once light is incident upon it. I mean, if you have a small solar panel, right, on a calculator, if you put a very bright torch to it, you would find that even without sunlight, you're able to use that calculator, even though you're using a prosthetic light, right? So that means it is not the heat. I mean, LED lights don't generate heat, right? So even without heat, light is still generating electricity for you, right? Then we have a sound energy, right? Uh, Sound energy can be delivered using speakers, right? We convert electrical into sound using speakers, and we convert sound into electrical signals using mic, right? So as I said, I did discuss this in detail over here, right? We call this a speaker. And then finally, we have nuclear energy. Now, please do not confuse chemical energy with nuclear energy, because in chemical energy, we react different chemicals together to get heat, right? But in nuclear energy, we are not reacting stuff. Instead, we are breaking the nucleus of an atom to release a huge amount of energy, right? We call those as nuclear reactions, right? And in those nuclear reactions, a lot of thermal energy is released, far more greater than any combustible material can ever produce. It is said that 1 kilogram of radioactive nuclear material can generate heat up to 1 ton of coal. So that's the difference between the generation of thermal energy compared to chemical reaction versus nuclear reactions. Also, chemical reactions release carbon dioxide, which is causing global warming. On the contrary, why nuclear reactors are becoming more important is because they generate not clean energy, I would say, because they do have their own side effects which nuclear hazards and nuclear radiation hazards are there, right? But if we talk about carbon dioxide release, then in that case, nuclear energy can be termed as green energy, although it has its own defects and issues to deal with, right? The handling of the nuclear waste is a big problem because that is not to be left around. It's not a coffee cup, disposable cup that you can just throw around and nothing will happen. It is dangerous material, so you cannot leave it out. It's harmful for animals, plants, and humans alike, right? It can damage the atmosphere very, very much. So nuclear has its own issues to deal with. Now, this is we have discussed this in a lot of detail how these different processes relate to each other. I gave an RA for this as well, but I only saw one RA submitted back to me, right? So I'm just going to move on with this topic because it's just a discussion topic. I'm not going to give you any questions on this because the if you already understand the topic, then I don't doubt any question is going to be troublesome for you, right? Now moving on to the last idea, which is evaporation and boiling, right? Over here, just let me zoom it up a little bit. So when we talk about evaporation and boiling, now we usually take these two as related terms, but they are not related. Why? Because when we talk about boiling, we're giving intentional heat, right, uh, to the system, which causes the rise in energy of these particles, causing it to bubble out and convert into vapors, right? So let's take the example of water, right? So it will uh, you know create these bubbles, while in terms of evaporation we only see escape of vapors from the surface, right? So I did discuss this in class. I made the chart, uh, you know so I'm just going to make a chart over here, right? Versus boiling. So I'm going to write this chart down. I'm not going to express much in the diagram, right? So boiling, in boiling, only occurs at surface, right? Uh, Happens throughout, right? That means once you start boiling, you see bubbles coming out from the walls, the base of the container, while in evaporation, we only are concerned with the top layer. And it's now when we talk about the rate, it's a slow process. It takes a lot of time for a liquid to evaporate, especially pertaining to the fact what is the temperature outside the ambient temperature. On the contrary, boiling is a fast process, right? If you start boiling a liquid, you won't be able to see liquid after a little while because all of the liquid will be converted into vapors at higher temperature compared to evaporation, in which some of the layer is going to move out. So if I look at this, once it's going to start vaporizing after evaporation, you're going to find that some of this liquid is going to be lost, right? So let's just say this amount of liquid will be lost in evaporation. So we are going to find uh, reduction in the volume of the liquid, but this is going to be a very, very, very slow process compared to boiling, in which the process is going to go a lot faster, and you will find that all of the liquid will be converted into vapors, and you will find a very fast fall in the level of the water, right? The volume of water will decrease very, very quickly, right? Now, when we talk about intermolecular forces and other stuff, the temperature, right? First, let's list the temperature. Happens uh, at all temperatures, right? Temperatures between uh, solid and gas, right? So that means, for example, for water, that range is going to be from 0 degrees Celsius to 100 degrees Celsius. Any temperature between these two is going to have evaporation, right? The particles will keep on leaving the surface of the liquid, and that is how evaporation is going to happen. While in boiling happens only at boiling point. That means the temperature is fixed for boiling, right? So only happens at boiling point, right? That means uh, if you start boiling a liquid, it is not going to increase the temperature, which we discussed in the temperature curve in the previous topic, right? So that's why we don't see an increase in temperature. Now I'm going to quickly go back to that diagram. Now over here I'm going to signify that evaporation is going to be happening. Here I'm going to write this right. So this is the point where you're going to have evaporation, right? And over here we're going to have boiling, right? So this is the difference between evaporation and boiling. Now I think this diagram is much more a much clearer picture of what evaporation and boiling is, and how they're different from each other, because this cooling curve clearly states that evaporation is entirely a different process compared to boiling, right? Usually we think of it as the same, right? But it's not the same, right? And we just discussed that, and this is the difference that we're trying to note it out, right? In terms of uh, you know uh, the energy. And the final thing that I'm going to discuss over here is the provision of energy, right? The energy of the particles. So in uh, evaporation causes cooling. And why it causes cooling? Because high energy particles leave the surface, resulting in loss of heat, right? That means or energy, right? If the total, since we are not providing extra energy, right? If you look at it, I'm going to say no extra energy given, right? Compared to this one, in which we are giving extra or external, right? Energy. So if we, in comparison to boiling, there isn't any loss of temperature, because as I said that in boiling the temperature remains the same. The energy is not lost, as it is provided externally to compensate for loss, right? So in other words, if the energy is lost, uh, then we provide it using external source. So these are the four major differences between evaporation and boiling. Now I'm going to simply rush to the end of this video, because I think it's getting a little too long, and you guys won't like this, right? So I'm just going to summarize and finalize the final topic, which is a rate of evaporation. And we understand that evaporation is a process which is happening at all temperatures. So that means there's several factors that are going to affect the rate of temperature. Now let's just say if you have a big bowl filled with water, right? Let's just say there's this water inside it, right? So if you have big bowl of water compared to uh, a tube that also contains same amount of water, nearly, but the surface area is less. So more area versus less area, right? Which one is going to have more evaporation? This one, right? Why this will have more evaporation? Because we just discussed that Evaporation on the contrary happens only on surface, right? It's a surface process. That means the more the surface area, the more the evaporation is going to be there, and less surface area means less evaporation, right? That's area. So factor number one, area. Factor number two, the draft, right? Let's just say if you have two beakers, right? I'm going to put a bar in there. You have two similar beakers. You have same amount of water in them, right? But one is actually having wind blown over it, right? Please don't mind the color because I like OneNote having these colorful pens, right? One has air flow, right? Airflow. Which one is going to have more evaporation? The one with the airflow. Why? Because the particles which are evaporating out and they were supposed to create a vapor pressure on this liquid are now gone. That means the removal of water vapors is going to push the liquid to generate more vapors, right? We do know, we discussed this, that things move from high concentration to low, right? So if there's high concentration on top of the liquid, then very little vapors will rise up. But if we blow the air, then we are going to see an acceleration or increase in the rate at which evaporation is going to happen, right? And if I want to prevent evaporation at all, I just need to put a lid on this, right? Lid. So it will prevent all evaporation because now the vapors are stuck inside, and there's going to be some amount of evaporation being done initially, but then the amount of particles that go out will equalize the amount of particles that go in, right? So it is going to be a complete cycle. We don't say that evaporation is not happening in this case. Evaporation is happening, except the rate of evaporation and the rate of condensation is going to be matched up to a point that you will see some droplets on the lid or on the sides, right? But you won't be able to see a much consistent dropping of volume. So once the volume is a little bit dropped, after that that water level is going to retain there as long as the lid stays intact, because no water vapors are lost, hence no more evaporation is going to happen. So evaporation depends on how the water vapors are treated, or if they're flowing or not, right? So now moving on to the third difference, right? The third critical factor is ambient temperature, right? Let's just say there's water in one beaker, right? Over here. Another beaker has water, except I put this one in direct sunlight, right? So when I put this in direct sunlight, it is going to, increase the rate at which this is going to evaporate compared to this. And why? Light. Let's call this light, right? More vapors. And why more vapors? Because you're giving, again, there's more external energy available for this liquid compared to this one. So more energy, more evaporation; less energy, less evaporation, right? So before I conclude this, I'm going to add one additional topic to heat transfer, right, where we discussed these modes of temperature, right, in which I'm going to discuss uh, the effect of colors on heat transfer. Now, since we're discussing, uh, we discussed insulators and stuff, right? So why things get to be insulators and what really happens. Now I'm going to give you this question-based, query-based idea that, let's just say if you have two beakers, right? Let's do an experiment. If you have two beakers having water in them, right? Same amount of water, except on one I've put an aluminum foil on top, right? And the other one is beer. So this is uh, aluminum foil, right? This is water in there. This is glass beaker for both, right? And again, this is water, right? Let's just say I put light to this, right? So if I give light, right, we do know that these metal is going to reflect light, right? While in this case, light is going to go through, right? That means some of the energy from the environment will be absorbed and evaporation will increase, or you can say the temperature of the liquid is going to increase. In this case, light won't be able to get through, but because it will be reflected back by the metal surface, and the temperature is not going to rise. Okay, that's one thing. Let's just say if I had boiling water, right? I'm going to remove this. Now this was about light. Now what will happen if I add boiling water to both these beakers? Now the energy heat from this boiling water will again be reflected around, right? So if I put an aluminum foil, right, in terms of heat radiation, the aluminum foil won't be radiating, won't let much of the inner heat to go out. That is why you see those, thermal containers or thermal bottles that you're using, they're made out of metal and not just plastic, because the metal inside that bottle will keep the heat inside the liquid, while the external one will prevent external heat to get in, right? And in between, I'm going to draw that the thermal bottle over here, right? Compared to this one, because this will definitely lose heat into the environment, right? Easily, right? Until unless I put some insulator. The metal container that you use is actually made in two layers of metal, right? So I'm just going to make this, right? Now this is your, you can say, thermal insulator bottle, right? This is how the bottles that you use are made, right? So if there's water inside it, right, there's one metal layer. This is outer metal, outer, and this is inner layer, right? And in between the two, we maintain vacuum, right? Over here we have and vacuum, and by vacuum, that means once you create vacuum in between these two layers of metal. Now over here, if you remember, we discussed in the topic of temperature, sorry, yeah, and in the modes, that in vacuum only radiation can occur, and for that we're using metal to reflect radiation from inside into the inside and from outside to keep the radiation outside, right? Since there is vacuum, so there is no more solid and there's no more liquid left, right? So this what it does, it actually prevents conduction of heat, as well as prevents convection, right? If there was any gas in here, that would radiate energy here, but that energy will not be able to come out from here because there is no convection or conduction, right? So hence not possible, right? But on the contrary, radiation can still react, reduce the heat, but for that we're using a metal container and not plastic, so that this heat can stay inside it if it keeps on reflecting inside, right? So that's why you find that these thermal containers or these thermal bottles are able to retain the temperatures, whether high or low, for a longer time compared to other containers, right? Now that's it for this unit. I think I've covered most of these topics for your revision. Just go through this video and you'll be fine. If you have any questions, just post them in the comment or just send me a text message on my WhatsApp. I'll be able to respond to you guys, as soon as possible. Thank you for your time. Bye bye.